are on lesson 2 of the R Bootcamp. And I've gone back to the course page so that you can see where I'm going to, the course webpage that is. So you can see where I'm going to click and get the worksheet for this second lesson of R Bootcamp. So I'm going to click on worksheet and I'll save it in my documents folder or wherever you want. And now I'm going to go and start teaching off of the slides, but you could also look at this full text version of the lesson if you want to get more prose version of what I'm going to be talking about later. So let's go ahead and start lesson 2, working with data frames. So pretty much everything you're going to do in R when it comes to analyzing data is going to be using data frames, because those are kind of the workhorse type of object for organizing data, setting it up to input it into statistical models and any kind of model you want to do for the most part. So unless you're into, spatial data and all that kind of stuff, but everything is just kind of some form of data frame or other. So we're going to learn some of the basic ways to manipulate data in a data frame, and that we'll use in the rest of our lessons to do cool stuff like machine learning and different omics techniques and that kind of thing. But for now, we're just going to look at the basics. So we're going to import data. Mostly when you work with data in R, you're going to be importing it from some external file, preferably a CSV, a sort of text file containing data. We're going to learn what a data frame is and what tidy data means. In other words, there are different ways to organize data in a data frame, and tidy data is the way that works well with most statistical models. We're going to kind of do some basic manipulations on data frames, reshape them, and we're going to calculate summary statistics of our data by grouping it and get summary statistics on each group. A very common thing you might want to do. So what is a data frame? We've seen, I think I mentioned it in the last lesson, but we didn't actually see any data frames yet. It's basically R's way of encoding a table or spreadsheet of data into an object that you can work with. So data frames are kind of two-dimensional. They have rows and columns. Each column has its own data type. So like there could be a column of all numeric. Like each column is a vector. We've seen vectors already. A data frame has vectors for its columns. So each vector has to have all the same data type in it. So one column in your data frame has to be all numeric. One is all character. One could be all factor, and so forth. And ideally, each row in your data frame is an individual observation where each column is a variable. Like if column could be sex and be a factor, with male and female be the levels. It's the sex of each observation. Then you might have body weight, as another column, which is a numeric, for example. Now, we are going to be using functions from a package, or it's really a group of packages that you can load all as one package called tidyverse, which is a set of packages that are designed to work together to make it easy to wrangle and manipulate data in R. Now, you don't have to use tidyverse packages to do data manipulation in R. There are functions within basic R without loading any packages that will do what we're about to do. There's also a package called data table that can be used to do what we're about to do. But to be honest, tidyverse has kind of become very common in the last few years, so it's very widespread. Most of the learning resources you'll see are using tidyverse. I think it is kind of easier for beginners in a lot of ways, and so I recommend starting with it. But also, if you become a big-time R programmer, it's important to learn all the ways to work with this data, but tidyverse is a good starting point. So we're going to start by importing data from a CSV, and I've put this this CSV on the web page, so you can just read it directly from the URL. Although in practice, usually you'd be importing data from somewhere on your local hard drive. And we're going to use this read underscore CSV function from the tidyverse package readr to import the data frame, or to import the CSV file into a data frame. And it's a special kind of data frame called a tibble, which is a tidyverse special kind of data frame that has extra features that makes it easier to work with and manipulate. So this is I'm going to call this data the object SMammals, small mammals, or SMammals, because it's a data set of measurements taken on a bunch of small mammals. It's if you're an ecologist, you might know about the project NEON, which is a set of ecological monitoring stations set up around the United States that all measure the same ecosystem and living organism variables. So there's like a bunch of locations around the US where they measured a lot of things, including they trapped small mammals and measured their body measurements. That's the example data set we're going to be working with. So let's go ahead and go into RStudio. By the way, I think whenever we do a new lesson, I would recommend restarting everything from scratch. So I'm going to go to this session up here and say restart R. I have it set to delete all variables in my environment and not have any packages loaded, so that we can kind of know we're starting from a clean session every time. That's what I recommend doing usually. So I'll close this worksheet from the last lesson, and you can save your changes if you want. There are cows and chickens again. I'm going to go ahead and open the lesson 2 worksheet that I just saved onto my hard drive. And now I'm good to go for lesson 2. The first thing I'm going to do is load the tidyverse packages by typing library parentheses tidyverse and hitting Control Enter to run that. It will load all the tidyverse packages, give me a bunch of little messages, which basically mean everything is good. And then I'm going to use the read underscore CSV function to, as long as you're connected to the internet, which you must be if you're talking to me, read this CSV with data in it from the URL. So I'll hit Control Enter on that too. And it gives me some information about it prints information about what the import process, in addition to creating this object in our environment called SMammals. It says it's got about 1,600 rows, 7 columns. The names of the columns, some columns are character, 5 of them. Some columns are DBL, double precision, means a numeric variable basically that has a decimal point after it, double. So, and also you can see that in our environment, we have next to the name of the object, there's this blue arrow. It's a nice feature in RStudio. You can click on that and it will give you information about the columns, like what is the name of each column and the first few values and the data type. So like the site name, the species ID, and so forth. Is anybody unable to get to this point? Or are we all good? Okay, so what can we do now that we've imported this data frame into our environment? What are we going to do with it? Well, if you type the name of the data frame in your console and hit Enter, it will print the first few rows of the data frame and some information about its dimensions. It won't, well, the tidyverse by default will not print all the rows because some data frames have millions of rows, so it would not make sense to print them all by default. Of course, if we really want to, we can. You could use the print function to print a specified number of rows using the n argument for the number of rows. So we'll start by just typing SMammals into our console, or you could I have it already here. You can hit Control Enter here, and it will just, if you just type the name of the variable in, it will give us the first few rows, right? And tell you more information. We can use the print function, specifying the argument n for how many rows we want to print if we want to see more than the default of 10. There we have more rows. So far, so good. Okay, now what if we wanted to pull out specific subsets of data from the data frame to work with them? We can do that by row or by column. How can we do that? Yes. Well, first there are other ways to summarize the data frame. Before we start pulling subsets, there are other functions that will give you summary information about a data frame. Base R has a function called summary. There's also str for structure that will give you summary information. There's glimpse, and then summary also gives you information about missing values. So let's try summary, str, and glimpse in our console and see what they do. We can do summary, parentheses, S mammals. That's the name of it. It tells us what the different column types are. If it's numerical, it'll give us summary stats. It also says NAs. NA is R's code for a missing data point, a missing value. So there's 50 missing values in one column and 35 missing values in another, in the numerical columns. str can also be used. Yes, so it's just another way to look at it. Glimpse is another one you could use, which gives you the first, however many rows in a compact format. Those are just ways you can look at your data frame and see what's in it. Now, how do we pull out specific values from the data frame? Well, one way to do it is you can use the square bracket to pull out specific values. You use the syntax is the name of the data frame, bracket, the row number or name, and the column number or name. So if we wanted, for whatever reason, the second row, third column, we would use bracket 2, 3. And this will actually give us a tiny 1-by-1 data frame that corresponds to the second row, third column of that original one. Let's just do that just to demonstrate, although this is something you wouldn't do that often in practice. So it's the second column was family, and this is just the second row, and the third column is family, so it's giving us the family observation for the third row. Second row. We can get an entire row by leaving the column part blank, or we can get an entire column by leaving the row part blank. Like if we just put 5, it would give us the fifth row, all columns. If we did 2, it would give us the second column, all the rows. Let's just do that to show. That's row 5 of the data, all the data from the fifth observation. 2 is going to give us just a 1-column data frame with the species ID column, because that was column 2. Okay. We can also subset. We might not just want 1 row at a time or 1 column at a time. We could we've seen our number sequences before. 6:10 would be 6, 7, 8, 9, 10. They don't have to be consecutive, but in this example, they are. This would give us all columns from those rows, 6 through 10. You could also get a set of rows and columns, rows 1 through 5 and columns 1 through 2 at the same time if you wanted to. I'll just type those in just so you can see. 6:10, comma, means rows 6 through 10, all columns. So there's just some of the rows. And if we did 1 through 5 and 1 through 2, it'll give us the first 5 rows, but only the site name and species code. The columns in this data frame have names, so we can get columns by name, not just by number, which is actually a better way to do it because you might not memorize that taxon ID is column 2, and it might change later if you load in a different version of the data. So the best way to do it is pulling the columns by name. And so we can, instead of giving it a vector of numbers for the columns we want, we can give it a vector of names using that C function with quotes around the name. So like if we wanted row 20 and we wanted the species ID, the taxon ID, and the sex, we could do it that way, 20, comma, and then, so this one is a numerical, and this one is character for the 2 columns by name. Like just 1 row, and then we want in quotes the taxon ID, and no, it's case sensitive here, right? So taxon is lowercase and I and D are capitalized. That will not work otherwise, and sex is lowercase there. So that's the taxon ID and sex for one of those observations. Another way, you can pull out a single column from a data frame as a vector using the $sign. And so like if we wanted the site name column from the S-mammals data frame, we could put S-mammals $sign site name. The N is capitalized there. And yeah, if the column name has special characters in it, you have to put backticks around it, but you don't need to do that if it's just letters and numbers there. So that's how you would pull out one column as a vector, just like that. So there's you know, the first bunch of 1,600 site names. We can then take those columns and pass them to functions and do things with them, right? If we wanted to take a single data frame column and pass it to a function as input, we could do that. For example, so site name is a character variable, but there's only a few sites in the data set. Let's say we wanted to look at what unique values are in that vector. So what are the possible site names in the data? We can use the unique function to get that. And then the table function will give us, is also one you could use on a data frame column. It tells you how many values there are in each of the categories if it's a character or a factor variable. Or also it could be used for a numerical variable as well. We can use unique. Let's do it unique on site name. Control Enter. So here we see that there's, in this particular example data set, we have 4 unique site names in our data set. And if we wanted to know how many males and females there are, we would use table and use the sex column as our argument to the table function. And we have F, M, and U for unknown, female, male, and unknown, sex for those. Does anyone have any questions so far, or is stuck at any point? Okay, I'll keep moving on then. Now, another way to subset a data frame besides that bracketing way that I've showed you which is actually in some ways more useful, is to use the tidyverse function filter, which will give you subset of rows. Now we don't have to subset like, oh, I want row 20 or I want row 117. We can actually subset rows by condition. So remember in the last lesson, we learned about logical operators to say greater than, less than, and give you trues and falses. We can actually use that to subset the rows of a data frame. So like, let's say we wanted to do an analysis on all rodents or whatever that weigh less than 10 grams, there's a weight column, and we can use the filter function to get all rows where weight is less than 10. So the filter function, the first argument is the name of the data frame we want to filter. The second argument is a condition that we want to filter by. So like it's going to be something that gives us a logical. And so we're going to, and you can use columns that are in that data frame as part of that argument. So filter of S mammals, comma, weight less than 10 is going to give us a new data frame back that's smaller than the original and has only the rows where the weight variable is less than 10. We filter S mammals, comma, weight is less than 10. So yeah, and then it tells us it's 14 by 7. It only has 14 rows. Only 14 of the readings were less than 10 grams. Because their traps pretty much only catch adult mice, almost all of which are less than 10 or greater than 10 grams. Only a few are less. Oh, and I see that a few minutes ago, Grant put on the chat that he is in the help room on Zoom. So if people are stuck on anything, you can go to that link and he will help you out, hopefully. Where were we? Here we go. Another thing you can use tidyverse for is to pull out specific columns that you want. That's what the select function does. And the first argument to select is the name of the data frame, and any subsequent arguments are the names of the columns that you want. You do not need to use quotes on those. You just put them in directly as variable names. Like if we wanted the species ID and the weight columns only, we would use select for that. First argument, the data frame name. Every other argument is the names of the columns we want. So if we wanted S mammals, wanted taxon, ID, and weight, and hit Control Enter, you can see we get all the rows, but only 2 of the columns. So we're going to spend the next little while of this lesson. Yeah, Bara.
So I have a question. So can we put an AND operator between, like, if I need a taxon ID and weight?
You would not put the and for that because those are not logical. In the filter, you could do that. Like if you wanted weight is greater than 5 and sex equals male, that's where you'd put and because it's uniting 2 logicals together. But you wouldn't use and to select multiple columns because that's not a logical. It's just listing out the columns you want. So you would not use and for that.
Okay.
So we'll spend the next little bit talking about how to calculate summary statistics for entire data frames or for subgroups of the data. And in the process, I'll show you how to deal with missing values when you're doing that. So a lot of functions in R that calculate summary statistics will have a certain behavior where if there is a missing value anywhere in that vector, it will return a missing value for the entire summary statistic. Like if you had a numeric vector and you taking the mean or the max or the minimum of that vector, it will work fine if there's no missing values in the vector. But if there's even one missing value in the vector, it will give you a missing value for the whole thing. Like if your vector is 1,000,000 elements long and has one missing value, and you say, what's the maximum value? It will say it's also missing. I'll show you an example. Like here's a vector with 3 elements in it, and we're going to take the max of it. Okay, so I'll just we'll define the vector x. It's got 3 elements. Now I'll say max of x. Well, it gives us the maximum value, 12.2, right? What if I say x bracket 2 gets NA? That means I'm just going to, whatever the second element of x is, I'm going to replace it with an NA. So now our x is 5.3 NA and minus 8. There's 2 numeric values and 1 missing value in there. Now what if I take the max of that? It gives me an NA. It's a missing value because at least 1 value in x is missing. And this actually makes sense to be the default because it helps you realize when there are missing values that may have arisen unexpectedly, and you can adjust your code accordingly. I think it's better to do it this way. But if we want to calculate the maximum anyway and ignore missing values for the purposes of calculating maximum, so give me the maximum of all the non-missing values, we just have to add an extra argument to that max function or the mean or the min or any other summary function. And that argument is na.rm. So remove na values. And if we say na.rm equals true, it will give us the maximum ignoring any missing values of that vector. So we get 5.3, right? Because that's the maximal not missing value that's left. So that's just a something I had to explain before we go and calculate summary statistics on this data frame, because this data frame has missing values in it. And again, this would work for mean, min, max, and sum, as well as other summary functions. And yeah, so this is just showing us one way to deal with missing data, which is ignoring the missing values. There are other ways you could like do imputation or things like that. But for now, we're going to say, well, let's just ignore the missing data. Okay, now this is something that we're going to cover now for doing multiple manipulations on the same data frame in sequence. It's called the pipe operator. You'll see it a lot if you see any R code that uses tidyverse. It is favored by people that write their data manipulation code in tidyverse because it helps you sequence the steps that you're doing to manipulate your data in a very neat and readable way, with one data manipulation step per line done on the same data frame. The pipe operator is written as parentheses greater than parentheses, and what it does is it's like a pipe taking the output of one function, piping it in as input to the next function. That may not make sense. I'll show you an example here in just a moment. Like, for example, if you had the square root function, the logarithm, and the absolute value function all nested in each other, what really you're doing is you're taking the absolute value first, then you're taking the log of that, then you're taking the square root of that. But it makes almost easier to see if you start with your x, pipe it to the absolute value function, take the result of that, and pass it to the next line, which takes the logarithm, take the result of that, pipe it to the next line, which takes the square root. And people usually write this split across multiple lines. You can put all that on the same line of code or split them on multiple lines, but people usually like to split them out onto multiple lines. It makes it a lot easier to read. And, you know, in reality, scientists' software code is usually not read by anyone else except you. You're the only, unless you put it in a publication or something, probably no one else but you is ever going to see it. So, but that still means you want to make it very readable, because you might go back and look at it a year later and forget what you did. And the neater and cleaner and easier to read it is, the quicker you'll be able to figure out what you did and move on from there, if that makes sense. So let's use this pipe operator to calculate some summary statistics on the entire data frame. Let's say we wanted to know the mean and the standard deviation of the small mammal body weights from this data set. Well, we're going to use the summarize function, which the first argument of summarize is the data frame you want to calculate summary statistics for, and any following arguments are the summary statistics we want to calculate. But we're going to use the pipe operator to take this S mammals data frame, pipe it in. So the first argument is this is the S mammals data frame, and then the following arguments are take the mean of the weight column. We're going to make a column called mean underscore weight. Take the standard deviation of the weight column. We're going to call it SD underscore weight. Let's see what we get when we type this code in. So we're going to say S mammals, and we're going to pipe that. So take that S mammals object and pipe it into the next function, and that function is summarize. We're going to calculate summary statistics on it, the mean of the weight column and the standard deviation of the weight column. Hit Control Enter there. Well, we get NAs for both, because there was, as I already warned you, at least one missing value in each of those columns. So what do we do about that? What if we wanted to say, well, we'll just ignore those missing values and get the mean and standard deviation for anything that's not missing? Well, you can use filter for that to keep only rows where weight is not missing. And if you remember our negation operator, the exclamation point, we can say not is.na weight. That means keep only rows where the is.na weight is not true, meaning keeping only the rows that are not missing values, throw out the missing values. We're only going to keep, for the purpose of this summary statistic calculation, we're going to throw out missing values. So that filter exclamation point is.na weight will give us a vector that's true if weight is not missing and false if weight is missing, and keep only the trues. And then we'll take that result and we'll pipe it into the next step. So take our original data, step 1, get rid of missing values. Take the result of that and send it into step 2, which is doing summary statistics. Okay, that's how we're going to get rid of the missing values. So we'll do filter, exclamation point meaning not, is.na is the function that tests whether a value is missing or not. Now we can hit Control Enter. If our cursor is anywhere in that block, it will run the whole thing. Control Enter. Now we have our mean is 30.5 grams, and there's the standard deviation. So we've done the summary statistics, getting rid of the missing values. Everyone good there? Okay, awesome. I'll show you another way we could have done that without filtering. We could also have added extra arguments to the mean and SD function to say within them that we wanted to ignore the missing value. So this would be an alternative way to get the same result. If we added this na.rm equals true argument to both the mean and the standard deviation, you could do, but that is a more repetitive, because if let's say you had 10 summary statistics you want to do, you don't want to add NA/RM to each one. So it might be more efficient to get rid of the missing values, then do the summary statistics. But this, for now, this will give us the same result. So I'll run this just to show you it gives the same result. So here we have the same result there in another way. Just like in any language, there's many ways to say the same thing. In R, there's lots of ways to get the same output. Yes, question.
Yes. So Quinton, so so in the filter function, so I will put the data frame, right? S mammals, comma. Can I use weight equals to NA and then filter out all the not available?
The best way to test whether something is NA is the is.na function. The weight equals NA will not work. Yep, is.na is the way that you would get a logical for whether it is or is not NA. That's the way to do it.
Okay, so one more question. So if my original data frame, like if I replace the missing values with NA, in that case it works.
So yeah, if you have NAs and try to do summary statistics, it will give you NA for the summary statistic unless you remove those missing values or put NA/RM in your summary statistic function.
Okay.
Yeah. So missing values, yes, it's good to code missing values as NA, but then you just have to be explicit about when you're doing summary statistics, how you want those missing values to be treated. So we're saying, okay, we're going to ignore them for the purpose of this, calculating the mean and minimum and maximum and stuff like that. Of course, if all the values are missing, then it will give you an invalid value basically for the mean or minimum or maximum. As long as at least one isn't missing, then you'll get something. So I just showed you can use NA/RM as well. Another step you could put in your pipe is, let's say we didn't just want the mean of the entire data set. What if we have multiple species in here? So it might make sense we want the summary statistics for each species as a group. Well, there's an additional function called group_by, which tells us, okay, we're going to, now the pipe has 3 steps. We're going to take the original, oops, went back to the beginning there. Here we go. We're going to take the original data frame. We're going to filter to remove the missing values where weight is not in there. Then we're going to group it by taxon ID. So that means any future steps are going to be done separately for each group defined by the column with the species code, the taxon ID. So we're going to get the mean weight and standard deviation of weight for each species individually. So again, it's that exclamation point is.na weight, which we had before, and this group_by taxon ID. So you can see we have additional pipes because we have an additional step in the process. So now we have means and standard deviations for all the species. You can see that actually some of them even have NA for standard deviation, even though we got rid of all the missing values. Well, that's because there's only one observation for each of those species, and standard deviation is not defined when there is only one observation, because you'd have to divide by 0 to get a standard deviation when there's only one observation. So we still have some missing values, but those are actually make sense in that case. And this is just another example of some more complex arguments we can give to filter and group by to give us just more nuanced summary statistics. Like, for example, you could filter by more than one condition. You could either put a comma or an and operator between these. Like if we wanted all the non-missing weights and we only wanted one species, we wanted the PELE species, we would say taxon ID equals PELE. So only take the rows where the taxon ID is equal to that string. We can group by more than one grouping variable. If we wanted the sex and life stage, there's like juvenile and adult observations in there. So we could have, this will give us all combinations of sex and life stage, adult males, adult females, young females. And there's also this N function, which can be used to count the number of values in each group as well, which can be handy. So this is going to give us all the non-missing values for weight for this one species of mouse for each combination of sex and life stage and how many there are of each. That's what this is going to do. Right, so we say, okay, we want the exclamation point is.na weight to say get rid of all missing weight values. We want taxon ID equals Pele for the white-footed mouse. And we want sex and life stage. And by the way, if you start typing the name of a column inside of one of these pipes in RStudio, it will recognize the name of the column and give you a prompt. If you want to, you can just click on that and it'll finish typing the name. It just makes it convenient. Summarize. We want to use this N function with no arguments to get the number of observations. So then we have, yes, female, adult, how many there are, their mean weight. And you can see it even has missing value. So some of the data actually had missing values for the life stage, and it's treating that as a separate group as well. So these are like females, unknown, basically, or the life stage data is missing for those individuals. Any questions on this? Yep. And so again, I showed you that you can there's missing values in some of the grouping columns, and there's missing values for standard deviations with only one observation. Okay, and this is just, another example showing you can do even more pipes. Oh, and I just also wanted to introduce a couple more tidyverse functions in the process. There's two more functions I'm introducing here. Mutate. Mutate is used to transform individual columns by doing operations on them. For example, if you wanted to multiply a column by a constant to convert it into another unit, you would use the mutate function for that. And you can define a new column name. So it's going to just add a new column to the data frame based on the results of that operation. So like it's going to make a new column called weight in milligrams, which is weight in grams times 1,000. And arrange will sort the result by whatever column or columns you want. So what's it going to do? It's going to get rid of all the missing weight values, keep only one species, convert weight into milligrams just because. We're going to group by site name this time. We're going to take the mean of the weight of the white-footed mouse at each of those locations, and then we're going to sort it in increasing order of mean weight. So the site that has the lowest mean weight for that mouse species is going to come first. And yeah, you can do that all in one nested line if you want to, but this is kind of a nice way to organize it and say, okay, step 1, 2, 3, 4, 5. So yeah, mutate is used to transform a column. So weight times 1,000 is going to get a new name. Then we'll group underscore by name of the site. We'll get the mean weight again with our summary statistic, and then we'll arrange, sort it into increasing order. Control Enter. Now we have our 4 sites, the mean weight in grams in increasing order. Kind of neat. Okay, we only have a few lines of code left in our worksheet, so we're kind of getting close to the end, getting close to lunch, but there is sort of one semi-complicated thing that I still want to explain in here, which is how to reshape data. If you get your data in a format that isn't how you want it and you need it in a different way to input into a statistical model or some other program, how would you reshape the data? That's what we're going to talk about now. So this is just an explanation of what we just did. Okay, so I'm not going to use the small mammal example anymore. I'm going to use an example that is using an example data set that comes packaged with the tidyverse package, just because it's easy, or a couple of examples, I think, just because it's easy to work with. Okay, so the two functions we're going to learn is pivot longer and pivot wider. Pivot longer takes wide data and makes it long. Makes sense? Pivot wider takes long, skinny data with a lot of rows and few columns and makes it wide. Wide meaning it has a lot of columns and few rows. Long has a lot of rows and few columns. It's skinny and long from top to bottom. And this example comes from this book R for Data Science, which is kind of like a tutorial book to introduce you to the tidyverse and how to do all this data manipulation stuff, which you might find a good resource to learn from. Now, tidy, this is just like a weird term that the person who invented tidyverse came up with, but really it's a very common format of data that is needed for a lot of statistical programs. All SAS procedures basically require this form of data as well, and so do a lot of model fitting functions in R. GraphPad has its own weird way of doing it, since I know some of you use that, which is very unique and different from most statistical modeling programs. I don't understand why they do it that way, but it's kind of not typical. Most other ones do it in this tidy way. Tidy means each observation has its own row. So a row corresponds to a single observation. Like in the mouse data set, each row represented all the data taken off of one mouse. Like one One observation, a mouse trapped on a particular day, all the data that was taken from it, the one observation. Each variable has its own column, right? So like sex was one column, weight was one column, and so forth. And each value has its own cell. We don't have like multiple values stuck in one cell and pasted together in text. Each column would have its own cell. We don't have like treatment 1 block A in one column. We would have a column for treatment and a column for block separately. That seems obvious, but plenty of people give me data that are not like that. So that's tidy data. So here are some example data that we're going to look at them each. They all come from the tidyr package, which is part of tidyverse, and they all have the same data. It's the number of cases of a disease and total population for 3 different countries, Afghanistan, Brazil, and China, in 2 different years, 1999 and 2000. These example data sets will already come up if you type those names because they come built in with the tidyverse when you load them. Table 1, Table 2, and Table 3, they're called. Oh yeah, so that's the answer. So hopefully you didn't see that. Let's look at them and see which one or ones of them contains tidy data. Okay, here's Table 1. So if you type this in, you'll see the same thing as I do. Okay, Table 1 has a country column, year, number of cases of the disease, and number of population. Table 2 has country, a year, type. So that's a column indicating whether this count variable is cases of disease or if it's total population. And here's Table 3. It has a country column, a year column, and a rate column, which is a character variable, which is number of cases / the total population. Okay, so which of these, Table 1, Table 2, or Table 3, which one or which ones of them are tidy data, where each observation is a row, each variable is a column, and each cell has only one value in it? You can put it in the chat or speak up on this one. One, 2, or 3, or more than one of those. Anyone want to hazard a guess on this? I'll wait till someone, oh, here we go. Okay, yes, some people are saying Table 1. Okay, I would agree with that because it has, each row is an observation. It is the observation of cases of the disease in one particular country in one particular year. That's an observation. Table 2 is kind of like overly long because it has the observation of Afghanistan 1999 is split into 2 rows here. The number of disease and the number of people. And Table 3 is just weird because it's taking numerical data and sticking multiple values into one cell, and that is kind of hard to work with. Of course, if it was a continuous variable, a numeric variable, it would work. But this is, yes, this Table 1 is the most tidiest form of the data that we have. Now, if we had data in the form like Table 2 that's too long for us and we wanted to turn it into Table 1, a tidy form, how would we do that? We have data that's too long and skinny, we want to make it a little bit wider. Well, we have to use the pivot wider function to do that. The ID that has 3 arguments, ID calls. Well, the first argument is the name of the data frame we want to transform. The second argument is ID calls. That is the column or columns that have the identifier for each observation. So this is right. In our data we have identifiers, which is the country and the year, and the actual data are the number of people with the disease and the total number of people. So we're saying, okay, these are the ID columns that uniquely identify each observation, the country and the year. Names from means which column in our long skinny data is going to give us the column names in the wider data. It was called type. And values from is which value, which column in our long skinny data is going to be spread across those multiple columns in our wider data. So we want to take the type and count column and have a column of the counts of one type cases and a column with the counts of the other type. So that's why we use names from and values from. So we're going to make a table 2 tidied and pivot table 2 in that way. So pivot underscore wider is what we're going to use as the to make this long skinny, to make this 12 by 4 table into a 6 by 4 table. And we're going to say our ID underscore calls, the country and year are going to be used for the IDs. The name, the column in our long data that's going to become the column names is the type column. And count is the name of the column here with the data in it, which is going to be spread across those new columns. If we hit Control Enter and run that, our table 2 tidied, you can see it has 6 observations of 4 variables. If we type in its name, it looks just like the table 1 originally. And you can actually test that by saying all.equal is a function that will take 2 arguments and will say, are these 2 objects completely equal to each other? Sorry, do you have a question? So yeah, if we run this, we should see true, meaning they're identical. So yes, we say true. We've confirmed we've turned table 2 into table 1. Okay, last example I think before lunch is how to take wide data and make it long. And this is actually, I think, the most common thing you usually do, because when you're doing data entry, it's kind of annoying to enter into a long, skinny data frame. Usually you like trying to enter data in about the same dimensions as a computer screen, which is kind of wide, or you like wrote it on a piece of paper, which is sort of wide. And so most data kind of begins its life in wide form. It's easier to enter and look at. It's kind of, you can see it more compactly, but for analysis, we usually reshape it to a long form. So that's why oftentimes it's pivot longer that I use to take the original data and make it long and skinny for analysis. So this is like a funny other example data set of the top 100 songs on the Billboard chart by week for the year 2000. So I'm like in my 30s, so remember this stuff well. Some of you might be too young for it, but is another example data set in the tidyr package. And yeah, so you can use the summary tools that you now know if you wanted to like explore the data set and look at information about what people were listening to in those long ago days of 2000. But yeah, some pretty terrible music back then. You know, some was better than others. But anyways, you can type in Billboard is the name of this data frame. So you can type in Billboard into your console to see the first few rows of it. So we'll do that. Yeah, you can see that there's a column for artist, a column for the name of the track, which is kind of abbreviated, but and what date it entered the charts, and then what its ranking was on some of the different weeks out of 100. So these are like the top 100. So like this, yes, go ahead. Do you have a question? So yeah, this some tracks were like only in the top 100 for a few weeks, and then it's NA if they left out of it, and some were in it for a long time, that kind of thing, like 98 Degrees and, you know, 3 Doors Down and stuff like that. So anyway, how would we want, this isn't really the best format to analyze. We want it in the longer form. That's right, it has like week 1, week 2, week 3, all the way to week 76 as columns. So what are we going to do? Well, we want each observation to be a song on a particular week. Each observation is a song. Yeah, this is not really correct. We want the observation to be a song at a given time point, with the artist name, the name of the track, its date where it first entered the top 100 and the week at which the ranking was observed are the identifiers, and then the data value is the ranking between 1 and 100. So it's going to be very long and skinny data. How do we do that? We're going to use the pivot longer function. This has 3 main arguments. Calls, those are the columns that we want to take from wide and make them long. And the columns, well, we can actually use a shorthand here because there's 76 of them. There's week 1 or WK1, WK2, and so forth. You can actually use shorthand. Week 1 colon week 76 will mean all data in our data frame between where week 1 is and week 76. You could also use the minus sign to say which columns you're not going to pivot. But we're just going to show you how to do it with a shorthand here. Names underscore 2 is, okay, we have all these column names, week 1, week 2. What are we going to call that new column? We're probably going to call it week. We have to put that in quotes. If you don't specify, it will call it name. Values 2 means what are we going to call this, the column in which we're going to put the data. And by default, it's called value if we don't specify. What are we going to do here? Well, we're going to say, okay, which columns are we going to pivot? The combined week 1 through week 76. The names are going to be, the name of that column is week and the value is ranking. So it's going to take our identifier columns and then take every other and repeat them so that it will have a long, skinny data. Let's just show what, and the identifier columns are artist, track, and date entered, by the way. So we can either say which columns are we going to pivot or which columns are we not going to pivot and pivot all the rest. So we can say, okay, we're going to pivot underscore longer. The columns are C parentheses, week 1 colon week 76. So we're going to pivot all columns from 1 through 76. Names underscore 2 equals week. So the column names here are going to be turned into a column called week. And the values, all the numbers in this data are going to be in the data frame are going to be turned to a column called ranking. So right, this data frame right now is 317 by 79. Now look at what the dimensions are when they make it longer. It's now 24,000 by 5. So it's like taking all that wide data and made to a long, skinny data. So like here's one track by Tupac, which week it in the first week of January it was 87th on the charts, and then the next week it went to 82 and so forth. And yeah, and you could also specify what columns not to pivot, which are artist, track, and date entered, by putting the minus sign and then the C and put those names of those columns: artist, track, and date entered. And that's going to give us the exact same result. So yeah, the same 24,000 by 5. Okay. Yes, and there are other things you can do to manipulate data. A very common thing people do is joining 2 data frames together by matching up values that have the same key. Again, I don't have time to go through everything in one lesson, so that's something that you definitely will want to learn about if you're doing any data manipulation stuff, which yeah, you can look at the further learning resources that I have provided on the webpage for that. And a lot of times you might want to do operations on many data frames at a time, like a list of data frames. Again, the learning resources I provided have stuff about that in there. And that's all I have for this lesson. So yeah, in a second I'll take questions, but I'll just say that right, we're more or less on schedule. Why don't we? It's 12, a little after 12 Central Time. Why don't we meet again at 1:15? Or yeah, what do I have? Or let me just stop the recording real quick. There we go.